Hello, everyone. Welcome to the Oxford seminar. This week, we're hearing from Khyathi, who will be telling us about double categories, fragmented spacetime, and an AQFT. Get it away.
Today I'm just going to be talking about this double categorical construction that I've been thinking about for an algebraic quantum field theory. So this talk is sort of the result of like a lot of thinking I've been doing on how to make the math that I've been thinking about a little bit more accessible. So bear with me, it's a little bit experimental and a little bit weird at times, but yeah, I really hope that you enjoy it and it comes across. But anyway, so an algebraic quantum field theory can be represented as a functor. So what I'm going to start doing is to first define the source category for this functor, which is going to be the double category of Minkowski spaces, and the target category for the functor, which is going to be the double category of von Neumann algebras. And the way I'm going to be motivating this construction to make it as accessible as possible is I'm going to be pairing these constructions with scenes from my favorite Hollywood film of all time, Mulholland Drive by David Lynch. The reason I chose this movie is partly because it is my favorite movie, but also because I feel like the way that this movie is arranged, there's like a lot of different timelines, a lot of different characters, and a lot of different things going on at once that are seemingly unrelated and then later come out to be related that's happening. So I just thought that it's very much in the spirit of what happens in an algebraic quantum field theory. So that's why I thought that this would be nice. So after I define the functor, I'll just be talking about gluing and locality. I'll come back to what that is later on. But yeah. So the very first shot of Mulholland Drive is basically this woman. So she's in a car, and all of a sudden the car stops and there's this car crash. And she has no clue what's going on. And she's just so surprised because something has happened so sudden. But miraculously she survives this car crash. And it's really weird how she's able to do that because it just crashes in like full impact. But anyway, so for those who don't know, Mulholland Drive is in this like very unique part of Los Angeles that's like on top of a lot of hills, and you can get this like very scenic view of Hollywood. So she's just like staring at Hollywood at the night sky. And she's so clueless about where she is or what she's supposed to be doing. And she has no memory of what's happening because she's hit by amnesia. But although like she's not physically harmed, she has amnesia and she doesn't remember her name or who she is. So so I'm going to be throwing around the word fragments a lot in this talk, so I thought it would be nice to just define exactly what I mean by that. So we as human beings, we never really observe all of space-time. So like, for example, me, I would be able to like perceive whatever experiences happen to me, and I would be able to tell like what is happening with respect to me. But me or you, like we will not be able to tell what is like globally happening in the universe or like exactly why we are doing what we are doing or what that is in like the grander scheme of things or how we are contributing. So we never get to really know the global picture of things. The only rule per se that fragments are supposed to follow is that we should be able to coexist. Really almost nothing else. So yeah, fragment is sort of like this local space and this like global big picture of things. So yeah. So although this woman has like no memory of who she is or what she's supposed to be doing, something that stays intact no matter like how bad your amnesia is that you would have this like feeling of self-preserval and wanting to be safe. So she's in Los Angeles in the middle of the night, and it doesn't take a genius to recognize that the crime rate is obscenely high, even for a major city. So she sort of has to protect herself, and she doesn't know what to do. So she goes down these hills and she sees this really fancy apartment, and she decides, okay, I'm just going to break in for like over the night. I'm just going to like figure things out, and then I'm going to leave is what exactly her plan is. So she enters this apartment and she's just taking a shower, and then she realizes that when she goes outside, people are going to be wondering what her name is or ask her who she is, where she comes from. So she sees this movie poster, and there's this actress named Rita on the movie poster. So she decides to just adopt the name Rita and pretend that her name is Rita from now on. So for the simplicity of this talk, obviously I'll be calling her Rita from now on rather than just woman. So yeah. So now I'm going to start describing exactly what the source category is, which is this double category of Minkowski spaces. So the objects in this category are causally convex regions. So now Rita is inside this apartment and she has like no memory of who she is. But at the same time, she doesn't really get to know what's happening outside of this apartment or what is happening in the city or what is happening in a more global picture of things. So whatever happens inside this apartment sort of stays inside this apartment, and it's like this closed region. So what that basically means when I say that it's a causally convex region is that every causal curve from X to Y lies entirely in U. So a way to think about a causal curve is like every possible event from point A and point B is sort of a part of that spacetime. So that's a more intuitive way to think about it. And also for this talk, I will be assuming that the regions are in like this one-dimensional Minkowski space, which is basically one-dimensional space and one dimension of time. And yeah, so these will be the objects in the double category of Minkowski spaces. So next in the story, what happens is she's hiding in this apartment, and obviously at some point the original owners of the apartment are going to come in because you can't just stay in some random person's apartment for too long. So anyway, so the owner of this apartment is someone named Betty who's been given this space by her aunt. So she's coming to LA because she just like she wants to pursue her passion in film or whatever. So she meets Rita and she just assumes that her aunt has like lent out this property to someone else. So she meets Rita and then she gets to understand exactly what has happened to Rita. So they sort of have a conversation about this car crash that Rita was in. And Betty talks about how she finds herself in this apartment and all of these things. So the vertical morphisms in this category are going to be inclusions of regions. So now that Rita is inside this apartment, her like life inside this apartment is sort of a subset of much bigger things like Betty's life now. Now that Betty is inside the apartment, like whatever Rita perceives, like Betty now knows about, and there's sort of interaction between them. And also Rita's life is part of whatever's happening in the city or that particular area at that time. Or like the major storyline of Mulholland Drive as well. So yeah, so because of this reason, we choose the vertical morphisms in the double category of Minkowski spaces to be these inclusion mappings between causally convex open subsets. So now, after Betty and Rita sort of speak to each other and she understands that Rita has amnesia, they decide that they really need to find out what Rita's actual identity is. Because they open Rita's purse and they find like a shit ton of money for no reason, and there's this random blue key. So they have no clue what's happening or why. So they decide that they need to figure out what her identity is. But they can't just do that by sitting inside the apartment, right? So now there's like an entire change of space. They are going to go from the apartment to like outside the apartment so they can understand exactly what Rita's identity is. So that's what the horizontal morphisms in this double category of Minkowski spaces do. So you're basically able to move from one space to another space without really like getting rid of the causal rules or like really messing anything up. So they're just changing space, but at the same time, like everything is continuous with respect to that region. So these are basically what the horizontal morphisms in our double category will be. So basically it preserves all the mapping rules. It's just that you're changing space and you're going to a completely different thing. So yeah. One of the reasons I chose Mulholland Drive for this presentation is because, like I said before, there's a lot of random, unrelated things that happen in this movie that the first time you watch this movie, you're going to be completely confused about what the scene is doing here. But then you realize that it was foreshadowing the entire thing that happens. So anyway, so this is a pretty infamous scene. It's at Winky's Diner, which will come up later on as well. And this like guy who you see on the screen, his name is Dan. And the guy behind him is his friend. So he's at Winky's Diner, and Dan is talking to his friend about this nightmare that he saw the day before. So in this nightmare, at the back of Winky's Diner, there's this alleyway. And he talks about how he sees this big black hairy monster on the alleyway of Winky's Diner. And he's somehow convinced that this monster is real and actually exists in the alleyway of Winky's Diner. And he's just trying to like convince his friend of this. And his friend thinks he's being absolutely ridiculous. And his friend says, okay, why don't we actually go to the alleyway behind Winky's Diner and see if this monster is actually here? And the character of this movie thus far doesn't exactly make it easy for us to believe that there's going to be a random jump scare out of nowhere, but that's actually exactly what happened. And yeah, this is actually seen as one of TV's greatest jump scares of all time because of how unexpected it is. So this kind of helps us understand exactly what the squares in this double category is. So what I've done here is just I've sort of naturally included the vertical and horizontal morphisms that we have. So if you take a look at the vertical morphisms here, they're both inclusion maps in the sense that whatever dream or fear he's having still remains inside his present self at Winky's Diner. And also the imagination or set that he feels in the real world is also present when he's at the alleyway. So these are like inclusions in the vaguest sense possible. And if you look at horizontal morphisms, there's all of this evolution from like it just being a dream that he's seeing to it actually being an imagination. And on the bottom end, there's like this sort of change of space that he's going from the dino to the alleyway. So yeah, hopefully that motivates exactly what the two morphisms are like.
That's a
Yeah.
question. So, just as all these events take place within LA, are all these open sets here, these huge causally complex sets, are they all in one big space time?
All right. So this is just a summary of our double category of Minkowski spaces. So the objects are causally convex regions, the vertical morphisms are inclusions of regions, the horizontal morphisms are causal maps between regions, and the squares are basically the commuting diagrams that you get as a result of this. So yeah, so now I'll move on to exactly what the double category of Von Neumann algebras is. So again, this is a completely unrelated, or that first seems unrelated scene of Mulholland Drive. There's this guy, Mr. Locke, and he's sitting in this cubicle, kind of like we are right now. And except that he's like the only person in the cubicle, him and his assistant. So he's in this cubicle. And for some time in this shot, it's just like complete silence. And then he picks up his telephone and then he calls someone, and then that person calls someone else, and then that person calls someone else. And this like chain of phone calls keeps happening. And we don't exactly know what is happening, but Mr. Locke is clearly being affected by it, and he seems like more unnerved and like more sort of upset in a sense. So yeah, the objects of the category of Von Neumann algebras are actually Von Neumann algebras. So what this basically means is, for those unfamiliar, most of the operations and like observables in quantum mechanics lie in this special type of vector space called the Hilbert space. So a Von Neumann algebra is a special type of C-star algebra that's in this like bounded Hilbert space, and it's complete and closed under composition. So sort of like Mr. Locke in his room, like he's like completely unaffected, like it's hard for things outside of this room to really be affecting him. But at the same time, there's this like phone that he's able to use, and he's able to like call people on. So this is sort of like an operation happening on him because it is like sort of changing his mood. But it has nothing to do with what is happening outside of the system. It has completely to do with what kind of system he's in. So yeah, this Von Neumann algebras basically encode all the observables for a given space-time region. So in this case, like Mr. Locke's cubicle or where he's staying. So Mr. Locke is actually the head of this production company, and the production company has this director employed, and he wants to make this movie called the Sylvia Nott story. And he has this actress in mind who he wants to cast for this movie. But there are these people who like want to offer some money for him to make this movie, or basically trying to bribe the director to basically cast the actress or someone who they want, and that someone is Camellia Rhodes. So the Castiglione brothers are here in this scene to sort of convince Adam and his directing company that they need to cast Camellia Rhodes for like the main character of the Sylvia Nott story. So for simplicity, I'm going to be defining the horizontal morphisms first and the vertical morphisms next. But the horizontal morphisms in this category are going to be something called Hilbert bimodules. So the more intuitive way to think about Hilbert bimodules is that, and you will notice that they're actually Hilbert MN bimodules. So say you have like a Hilbert algebra of like M or something, and you have under algebra N, and you sort of want a way to like translate between the visions of these two algebras into a single algebra using like a left and right action. So the way you would do that is sort of having the left action and the right action, and like having it translate to one single algebra, and that single algebra would be the Hilbert bimodule. So connecting back to the scene, there's sort of this tension between Adam's vision for what the Sylvia Nott story is supposed to look like, and also the Castiglione brothers' vision of what the Sylvia Nott story should look like. So they sort of have to come in between themselves and find a way where the film can still happen, just changing the representation of who the actress is going to be in the lead. So yeah, so Adam must now like work in a framework that just respects the brother's choices, but also doesn't completely ruin his artistic vision. So now this news goes to Mr. Locke, who is the head of this production company, and obviously he wants to be making a lot of money. So he doesn't like the fact that Adam is pretty stubborn about not wanting to change who his main actress for the Sylvia Nott story is. So Mr. Locke doesn't like that because he wants the production agency to get more money. So it's his assistant who's delivering this news to him. And Mr. Locke is pretty annoyed at his assistant because he thinks his assistant has not done a good enough job of convincing Adam of exactly why they should be casting a new lead actress. So the vertical morphisms here are normal unital style homomorphisms, which basically it just means that you're going from one Neumann algebra to another, but you're just respecting its structure with respect to multiplication and adjoints. So now Locke's instructions, which is like one system of beliefs, is like going to Ray, who has like his own algebra in a sense, and that's like the instructions are passing. So it's just like this passage of knowledge that is happening, but at the same time, like the structure is remaining intact to a sense. So yeah, that basically motivates what the normal unital style homomorphisms look like. And the square here is going to be perhaps the most infamous scene of Mulholland Drive, honestly, which is this cowboy. And this cowboy comes in the middle of the scene and he visits Adam. So this cowboy it's sort of implied, although it's not directly shown on screen, that the cowboy is sort of an employee perhaps of the Castiglione brothers, and he's just coming in to sort of make sure that Adam is casting Camellia Rhodes as the lead in the Sylvia North story, and he's not going to just go completely crazy with his vision and cast someone else. So the cowboy really doesn't give him a direct threat, but he says this perhaps my favorite quote in Mulholland Drive, which is, if you see me once, one more time, you did good. If you see me two more times, then you're in trouble. So that's what the cowboy says to Adam. And this threat, Adam sort of just conceives and understands, and he realizes that he is in some sort of pressure. So the way the squares work in this double category is through this thing called intertwiners. So these intertwiners are sort of this special morphism that acts between these Hilbert bimodules, and it makes sure that both parts of action coincide. So whether you have this like left action or right action, it's just making sure that what you get at the end of the day when you're like composing all of this stuff is going to remain intact. So this is sort of the thing that makes sure that the diagram commutes. So that's exactly what this intertwiner is doing here, which is sort of like this cowboy. Because at the end of the day, these Castiglione brothers have money. And even if Adam did not want Camellia Rhodes as the lead of the Sylvia North story, they would figure out a way for her to get the lead. So it's sort of like that. Like the intertwiner makes things inevitable in a sense. So yeah. So an example of this is this commuting diagram where, like in the vertical morphisms, you can see the production's options goes to the producer's picks, and the bottom diagram goes from Adam's option to Adam's pick. So there's sort of this influence, which is like the normal unital style, the horizontal morphisms, which is the Hilbert bimodules, which are sort of like trying to find a median between what the options that they want and the final pick that they can have, and these vertical morphisms, which are going from the producer to Adam on both directions, which is just normally under star homomorphism, so going from one algebra to another. So in this particular category, this particular double category, that is, I feel like the vertical and horizontal morphisms are worth talking about. The compositions of these are worth talking about simply because they are relevant to how we are going to be defining this algebraic quantum field theory and how we'll be talking about gluing and locality. So the very first thing I'll be talking about is the vertical composition. So now we are going back to the main storyline with Betty and Rita. So they go out of this apartment, and coincidentally, they end up at Winky's diner, which is exactly where the whole incident from earlier happened. So they go there, and there's this waitress, and the waitress comes by and gives them coffee. And Rita looks at the waitress's name tag and sees the name Diane, and something just goes off in her head suddenly, and she's like, "Diane, that name is like somewhat like familiar to me for some reason." So they open up this address book and they look for who Diane is, and they find the name Diane Selvin. And this sort of just rings a bell in her head. And she's like, oh, I think my name was actually Diane Selvin. And yeah, so Rita just, her like, yeah, she just ends up thinking that she's Diane Selvin. So the way the vertical composition in this category works is that, like I said before, the vertical maps are basically these normal unital star homomorphisms. So consider M to be like a knowledge algebra before the name Diane appears, and N to be like a knowledge algebra where she sees the waitress's name tag and she just hypothesizes that her name is Diane. And then P, the knowledge algebra where she opens the address book and she understands, okay, this is the address that I have to visit. So this is sort of like So there's like a map from M to N where she's like processing this name tag clue, and from N to P where she's processing exactly what address she needs to visit. So these sort of compose in the sense that after the name Diane appears, it's consistent that she goes and finds the address for her to visit. Yeah, so this is basically explaining that. So narratively, just this suspicion ends up in her finding her name and then the address. And then they end up deciding to pay a visit to her apartment, which I'll talk about in the next slide. Oh, so I forgot to define exactly what unital and normal means in this map. So what we mean by unital is that there is something that remains fixed no matter what, so how much the knowledge algebra updates, which is that the entire reason they're doing this is they want to find what Rita's identity is at. So that one main goal remains constant no matter how the knowledge algebra is going to change later on. So like the baseline facts and like whatever they know about themselves and also just uncovering Rita's identity remains unchanged. So yeah, a normal basically means that like the small observations or like whatever clues they get about Diane's identity, that's sort of building up, and that's like not breaking the logic of the search in any way. So yeah, now that they have Diane's address, they decide to actually visit the address and like pay Diane's apartment an actual visit. So now both Betty and Rita are outside Diane's apartment, and they decide to actually enter and figure out who Diane Sullivan is and what she's up to. And a bunch of crazy events happen inside the apartment that are thankfully irrelevant to this talk. But yeah, so anyway, so the horizontal composition here is sort of still playing into this idea of like changing space in a sense, if you can notice, which is that you have this public knowledge at Winkies, and then you have this address info which lives inside this like book. And then finally you have like the algebra for Diane's apartment or what is happening there. And there's sort of this change of space. So that sort of plays into the idea of how a von Neumann algebra probably has something to do with the way we have defined spacetime. But yeah, I'll come to exactly what that is later on. But yeah, so basically there's this change of space happening, and the way we define composition for von Neumann algebras, this like Hilbert bimodule stuff, is through this thing called contribution, and I'll explain what contribution is. So the way contribution works is that let's say you have a Hilbert bimodule that balances like the C and A algebras, and under a Hilbert bimodule that balances the A and B bimodules. So once you do the fusion, you sort of have something that's like balancing the C and B algebras. So that's what the contribution does. So basically two like channels of like different contexts like become one, and they preserve each other's like left and right actions. So yeah, that's what contribution does here, and this ends up being pretty useful when you're talking about von Neumann algebras and algebraic quantum field theories in general. So yeah, that's just a summary of what a double category of von Neumann algebras is. So the objects here are specifically a special type of von Neumann algebras called factors. So what that means is that its center is trivial. And so the vertical morphisms here are normal unital star homomorphisms. The horizontal morphisms are Hilbert bimodules. The squares are intertwiners. The vertical composition is just a composition of normal unital star homomorphisms, and the horizontal composition is the contribution of Hilbert bimodules. So after they are at Diane's apartment for some time, they go to bed, and then Rita just wakes up in the middle of the night and she starts screaming "Silencio, silencio!" And magically Betty understands what she's referring to, and that's actually to pay a visit to this place called Club Silencio. So they go to Club Silencio, and the awkward thing about Club Silencio is that there's a bunch of performers there, but it turns out that they're just lip syncing, and the actual performance is just a recording, which is super weird and very trippy realization that sort of horrifies them. Because it has like a different meaning in like the context of the entire plot, but I won't get into that. Anyway, so now I'm gonna introduce this new concept called globularly generated double categories. So this basically is a way of taking the data and making something that's like having all of the machinery out of it. So now like if you consider like the minimum data in Club Silencio, it would be probably the recording, and making it into like a full-on stage performance. That's probably something like what the globularly generated double category is. So in order to like make sense of exactly what this is doing, we need to define a couple of things, which is a decorated bicategory or horizontal internalization. A horizontal forgot the word. Anyway, internalization and globular generation and the free lift. So we have to be like defining all of these things. So I'll start doing that now. So decorated bicategory is basically this pair of categories. So unlike the name suggests, it's not actually a bicategory in itself, it's like a pair of categories. So the first category in the pair is just a category of vertical arrows. And oh yeah, and both of these categories have the exact same objects, by the way. And the first category has just like the vertical arrows, and the second is a bicategory with the horizontal one cells of the arrow and the two cells. So yeah, so basically you're like sort of combining the up and down arrows and the left and right arrows, but just splitting them into like two separate kinds of categories. So now there's this new thing called a decorated horizontalization, which in a sense, it's not really an action, but it's sort of this thing that you can do to a double category to like basically just condense it down to like its actual category and its bicategory. So yeah, so what we are doing is basically like just keeping the tracks, like I said earlier, but we don't actually have like the whole global picture of what is going on. We just have a way of like separating the data. So yeah, that's what this does. So this decorated horizontalization is sort of a process of just like taking the data in this double category rather than like considering what's happening. So what the internalization problem means really is how do you build a double category whose like visible data is exactly what is there in this decorated by category? Like how can like so basically how can we make a full performance based on just a recording? Is sort of the question that we are asking here. So when is it true that this like raw data that we are having is actually equal to the kind of double category that you can make out of it? And it turns out the answer to that question is this thing called a globularly generated double category. But in order to understand that, first, we need to talk about what a globular square is. And in the most elementary sense, a globular square is basically like you can consider this commutative diagram where the vertical morphisms are just the identity and the horizontal morphisms can be anything. So in a sense, you can notice that only the horizontal data varies and like the vertical data stays the same. So globularly generated categories are basically just formed from like the vertical and horizontal composition of these sort of things. So the way you're able to like compose them vertically and horizontally is because since the vertical arrows in the first globular square is just the identity, you make this other kind of square where like the vertical morphisms are like the same thing and you make the horizontal go to the identity. So now you're able to compose these two kinds of squares and whatever category you get as a result of that is globularly generated. So yeah, this is sort of, so any sort of realization or any sort of category that you can get from composing these squares, there's basically some sort of strict double functor from this composition to the actual data that we had before in the decorated by category. So that's what this is trying to do. So in a sense, like this is a free globally generated double category since you can just like define this from whatever data that you have. So yeah, so if you consider the double category of Minkowski spaces as something that's globally generated, yeah, basically we just take the vertical horizontal morphisms and these squares that we defined earlier, and sort of just plug in whatever we got to what the decorated by category is supposed to look like. So here the first category would be the inclusions of causally convex regions, and the second one would be causal oriented preserving embeddings, while the squares are just the commuting squares between them. So yeah, basically you just use this thing called whiskering, which is exactly what I defined earlier, which is that because the vertical morphisms are identities, we just like consider the different square and try composing them. So yeah, that's what the double category of Minkowski spaces is built by. And similarly for the double category of Von Neumann algebras, it can also be seen as a globally generated category where B star and B are defined as follows. Yeah, basically saying what I used earlier. The only condition for this is that the interesting thing that arises as a result of this is because of the functor Q that's going from the data to like the globally generated stuff, the contribution is suspected. And yeah, we'll be making use of that for a lot of proofs of a lot of stuff that I'll be claiming later. But yeah. Yeah, so this is basically a way for us to take whatever data is there and make it into an actual like whole thing is what's happening. Yeah. So now I'm going to be talking about the construction of an algebraic quantum field theory, which, like I said before, is basically a functor in a sense. And this is sort of a turning point in the movie as well, in that they come back from Club Silencio, and there's this really eerie scene where Betty comes in, and there's this blue box that randomly just ends up occurring in Betty's hands. So she puts this blue box on Rita's bed and just leaves it there. And then she just disappears randomly out of nowhere. And then Rita comes and she sees this blue box and she remembers the blue key that she has. And she opens this box and it's revealed that everything we have seen thus far was just a dream by the original Diane Selvin. So yeah, that's something to like remember for what I'm going to say. So the white woman who I showed earlier, Betty, her name is actually Diane Selvin in real life, and she is the person who's been seeing all of these dreams. So that'll be relevant later on. But anyway, so the way this algebraic quantum field theory double functor is defined is the source is like the double category of Minkowski spaces, and the target is the double category of Von Neumann algebras. So the objects are basically you go from some region of spacetime to like constructing a Von Neumann algebra from it. So yeah, then the vertical morphisms are like inclusions to normal neutral star homomorphisms, and the horizontal maps from the causal maps to the Hilbert bimodules, and you can compose them via confusion. And yeah, the two cells basically map from squares to intertwiners. So now that you have like opened this blue box, everything sort of collapses into this one like single structure where you like understand that this is just a dream inside a person's head. So everything sort of just collapses to like this being in the real Diane Selvin's world. So yeah.
Can I ask a question? How do I think about the image, the Hilbert bimodule, which is the image of a
Yep.
causally modified?
The
The horizontal cases here, these causal maps.
yeah, so that sort of ties into like how you construct a Von Neumann algebra from the like actual spacetime. So the way you do that is basically you construct these operations on the spacetime, and the algebra of that becomes a C-star algebra, which is like if you're bounded by the category of Hilbert spaces, it becomes a Von Neumann algebra essentially. So yeah, the way you do that is basically just construct those and then construct the Hilbert bimodule between them. So
But
Yeah.
is there a way, so if I think of the von Neumann algebra, it's these sort of, it's algebra of observables, it's
the what?
the algebra of observables that are supported on this causally convex region, is that right?
Yeah.
And
So,
then,
like-
and then I have a causal map, like how do I think of this Hilbert bimodule?
Like the causal map between two regions, right?
Yeah.
And like the Hilbert. Okay, so you can think of the Hilbert bimodule as sort of just an algebra that's like trying to resolve the end and starting points of that causal map in a sense, and like whatever is happening in that like part of events or whatever. It's basically in a single algebra. Yeah. Yeah. Does that make sense? So,
Yeah, thanks.
Yeah, I thankfully I think I will be talking about that in the future. So yeah. Wait, what? Okay. So yeah, so an algebraic quantum field theory at the end of the day is still supposed to satisfy certain kinds of axioms. So the interesting thing about an algebraic quantum field theory is that most quantum field theories you can't really generate axiomatically, but this is one of those quantum field theories that you can absolutely make from axioms. And these axioms here are called the Hart-Kastler axioms. So this is isotony, locality, covariance, and time slice. So what isotony means is that if there's like this region inside under region, all the observables in that region is also inside the observables of the other region. And yeah, so space like U and V means that they're disjoint spaces and like they have nothing to do with each other. Then that basically means that whatever is observable in U and whatever is observable in V also have nothing to do with each other. And covariance basically means that the symmetries act by natural isomorphisms. And the time slice means that if U contains under Cauchy surface V, then the algebra of observables of U is the same as that in V. So the box, it doesn't really reveal what reality is, but it sort of collapses the dream into some sort of structure. And this is sort of like an AQFT net. So what an AQFT net is like, if you consider just like one particular like subset of spacetime rather than like all of spacetime, and sort of just see what that particular subset of spacetime is mapping to. That's sort of what an AQFT net would be doing. So yeah. So now I'll be talking about gluing and locality and what that is in this algebraic quantum field theory. So now we are sort of at this transition where we have realized, oh, this is actually a whole dream that's been happening in someone's head. And this cowboy comes in again, and he's like sort of waking up Diane, the real Diane, and telling her to like, hey, wake up, pretty girl. You need to wake up and do stuff. So yeah, he stands inside her door, like comes inside her room, and then he just leaves, and he has this frown on his face, presumably because he's just upset that Diane wants to be stuck in this dream and doesn't want to come back to reality for also worldly reasons that again I won't get into now. But yeah, so intuitively the way to see this is that there's sort of this matched shadow space that's happening here. So first the cowboy smiles at Diane and tells him to wake up. And then there's this shared anchor where there's like the same doorway frame and there's the same room and everything. And at the end, the cowboy is just closing that door and leaving unsmiling. So we can do all of this even though there's some sort of shared space between these things, even though like the reaction of the cowboy completely changes and the context of the scene completely changes. We can keep all of these things in some sort of shared space and have it not like break causality in any way. So that's basically what gluing allows us to do. So yeah, you can have this entire sequence of things as one coherent thing. So yeah, the way gluing works in an algebraic quantum field theory is you consider a net from OFM to VNA from the functor that we defined earlier from the double category of Minkowski spaces to the double category of one Neumann algebra. So the rule for gluing is that if U and V are like disjoint of each other and they're not like sharing any space, then inside T, which is where U and V lives, then the images of A of U and A of V commute. So what that basically means is that by A of U existing or whatever like algebra of observables that we have existing because of U, and whatever algebra of observables we have because of V existing, they don't contradict each other's existence. So that's basically, so the way you prove this is that you like match on the overlaps using this thing called compatibility, and then you like use the independence rule, which is that if U if V is equal to 0 for this join U and V, and then you construct using this push out square, this sort of universal algebra A of M using all of these properties. And yeah, basically you just take the co-limit over this compatibility thing. You write M as like this union of a bunch of other spaces over A, and then you quotient that out by whatever overlap is there and whatever is disjoint. And yeah, so you basically end up getting a pretty clean space, but there's a caveat to this that I'll discuss later on. But anyway, this is sort of a general diagram of how it's not a perfect diagram, my bad. Anyway, but yeah, so the way this works is that let's say you have M that's U union V and W that's U intersection V. So you sort of want whatever is U union V, but without the repetition from the intersection and for everything to just like go perfectly. So yeah, that's sort of what we are doing here. This push out square just like make sure that the gluing is intact. And yeah. So yeah, now I'm going to be talking about locality. And now that Diane is up and awake, she has to like go on with her real life. And in her real life, she's just this very miserable human being. And she's clearly going through something and she's very depressed. And her neighbor is coming in and she knocks on the door and then she's like, Diane, you haven't been picking up my phone calls for a long time. And yeah, so she just tells Diane that she's basically Diane borrowed some stuff from her neighbor. Her neighbor's name is Divosa. So anyway, so Diane owes some stuff that she's supposed to give back to this neighbor, but she hasn't done that yet. So yeah, the neighbor is just asking her to give that stuff back. And she hands over this blue box. So, anyway, then Diane goes back inside her room and then she starts making coffee. Um, Anyway, so what locality is trying to do is that what is happening like outside of Diane's room, where like her neighbor is asking her for stuff and her making coffee are completely independent of each other and they have nothing to do with each other. So even if they like completely change the orders, it doesn't really do anything as far as the meaning of the story goes. So the thing about David Lynch and the beauty of Mulholland Drive in general is that there's some rumors from the cast that they basically just saw David Lynch like take a bunch of random scenes and just cut them in the most confusing way possible to create this very random story that's confusing. Which yeah, sort of plays into this idea of that like if you just like reverse the order of the scenes, it would make as little sense as it did before too. So yeah, that's basically what this does. So the order doesn't change meaning in a sense, is sort of what this locality concept is trying to say when these things are disjoint. So again, let's have U and V inside T, but they're like disjoint. And what you're trying to say is inside of A of T, the images of A of U and A of V sort of commute. So the model for this is again using our double category of Minkowski spaces to the double category of von Neumann algebras. So you use this sort of interchange law of double categories, which is basically trying to say that like the square of the square, how that commutes, is equal to like how the square of the square like sort of commutes on the other end, sort of. So yeah, you basically just make use of that and say that if you did U first, so like whatever happens in U first and then V, sort of as like in a more like star algebra point of view, whatever like operations happen in U and then V, or V and then U, sort of like nothing different will really happen. So yeah, this is sort of the diagram for that. So yeah, let's say you have X in A of U and Y in A of V. Then yeah, the way you like sort of get the elements inside the image from this, the order in which you do that doesn't really change anything. Yeah, so now I'm sort of just going to explain why I think double categories are better for this algebraic quantum field theory and not something else. So there's this blue key sitting on Diane's table doing nothing, but this blue key sort of like tells us as the audience that something very bad has happened to the real Camellia Rhodes, and the real Camellia Rhodes in real life is actually Rita. So this blue key sort of implies to us that Diane has done something that's probably not her proudest moment to Camellia. And this blue key is sort of a signal of that to the audience because we don't get to see what actually happened, but we just see this blue key. So this signaling thing is pretty important in quantum field theory in that there's this entire like construction by Salinger and some other people called completely positive maps. So the way these completely positive maps work is that they represent exactly the kind of operations that you're doing on this Hilbert space. And there's a whole other construction of that. But basically, what this means is that in a one category, you have this limit that you will only be mapping these inclusions to star homomorphisms, and there's no place for things like completely positive maps. So the way we have defined the horizontal morphisms, especially in the von Neumann algebra category, is such that the horizontal morphisms are Hilbert bimodules. So these Hilbert bimodules can actually secretly be written in terms of completely positive map stuff. So that sort of gives us that point of view there, and we don't completely lose that. Yeah, and at the end, there's this like huge dinner party going on, and the real Camellia Rhodes is sort of inviting Diane Selvin to, sorry, I couldn't find a better quality image, but so basically, so Diane Selvin is going to Camellia Rhodes' home, and the driver is dropping her off at the location, and she's completely confused because she's like, I've never been to this place before, but then Camellia Rhodes comes in, and she's like, oh, this is just a shortcut that I told the driver to take, so you can get here sooner. So she sort of just like directs her across these woods. And the whole time Diane is super paranoid that Camellia is going to hurt her in some way. So anyway, they go to this dinner party and you sort of have this notion of a route and a shortcut. So another reason why I think that the double category thing is better is like you mentioned before, is sort of like because you can map the composition of these like causal spaces like to these Hilbert bimodule stuff, you sort of get to know exactly the algebra of the part that you are taking and how that behaves in a bigger picture rather than just know the root like and exactly how the mapping works. So I think having like an algebra attached to things and like having a lot more data just like really helps like further the purpose of exactly what an algebraic quantum field theory is supposed to do. So yeah. And okay, this is not the final scene of Mulholland Drive, but the penultimate scene of Mulholland Drive is this dinner party where there's Camellia Rhodes and there's Diane Sullivan, and they're in this dinner party. And this dinner party is like a super overwhelming scene for the audience who's watching this film because a lot of things that we believe to be true up until this point of the film are just completely wrong, is what we realize from the scene. So it turns out that Camellia Rhodes is actually dating Adam in real life. This on the whole thing. But anyway, so there's a lot of other realizations that Diane, we see Diane come to basically. There's a lot of different conversation. The way people interact with each other are completely different than what we would have assumed them to be because we're still sort of veering off the dream portion of this movie. So another reason why I think double categories are good is that you sort of get to see the complete interface of how these algebras are behaving with each other. So through these bimodules and like because you can compose them through this confusion, we can sort of have this like notion of like Morita equivalence sort of like as a part of this double category construction living in much more naturally. Whereas in a one categorical construction, we could have like this natural transformation thing. I mean, it's not that we can't have a multi-equivalence. It's just would be much more concept than it is in a double categorical setting. So yeah, before I go to the summary portion of this, I just want to thank some people for making this talk possible. First and foremost, my mentor and one of my closest friends, Matthew Gurman, for listening to a lot of this talk and also just listening to my rants at his office for like 2 years straight. This year has not been my greatest. I've been through a lot and I'm very grateful to be here and to be able to give this talk. And second, I want to thank Emergent Ventures for giving me a grant that allowed me to come to Topos and for also finding a benefactor to fund my education. So a big portion of stress is relieved from my life and to Topos Institute because ever since I started interacting to people from Topos, I got a much bigger vision of what I wanted to do in life. And yeah, so I'm just very grateful. Thank you for hosting me. So yeah. So summary of what I've discussed thus far is that there's this double functor that goes from the double category of Minkowski spaces to the double factor of one Neumann algebras. And I described exactly what that functor does or what the idea is and exactly what a local net is. So that's basically just like taking the specific portion of spacetime and studying the one Neumann algebras linked to it, and also what locality does, which is like just seeing that two different spacetimes can sort of exist without contradicting each other, and gluing, which is sort of just putting these two spacetimes that have nothing to do with each other totally together. So yeah, that's basically what I've talked about. So the future work that I want to do is that gluing is traditionally actually represented so this left Khan extension sort of thing, but I haven't figured out exactly what that would look like in this double categorical setting. And yeah, just see if there's like a more interesting proof perhaps of the other High-Castler axioms that I can make from this setting, but that's not too important because it's already true from what we have directly, but yeah, I just want to see if there's something more interesting that we can do. And maybe just find more examples where this more like concrete examples where this setting could be useful and just check some other properties of this thing. And the one that I'm personally most excited by is that there's this entire book written by Selinger on quantum lambda calculus. So like this is pretty like useful for like a computational model of quantum mechanics. So there's this very interesting paper by Cho and Westerburn where they sort of model this quantum lambda calculus idea using one Neumann algebras, and they are able to extend this to like infinite dimensional stuff, which is pretty cool and interesting. So I want to see if that can really be applied to whatever double category thing I have now. And yeah, just maybe check some other stuff. And one Neumann algebras are then also well behaved. There's a specific type of one Neumann algebra called type 3. And yeah, that's like the poorest behaved one Neumann algebra ever. So I just want to see if this AQFT can do something regarding that. And yeah, that's it. These are my references.
Great, thank Khyathi for that. And have any questions?
Yeah.
So you described some of these axioms about local nets.
Yeah.
Is the claim that those are implied by just being double functorial on the Minkowski?
Yeah, and the way that the double category is defined. Yeah.
Okay, so there's no extra conditions on that double functor, it's just a double.
Yeah.
That's good.
Yeah.
Talk more maybe about what you mean by operatic left Khan extension.
Yeah, so the reason I haven't done that is because I'm not sure myself.
Okay.
But yeah, that's something to think about. Yeah, actually, Schreiber has this paper where he just like talks about algebraic quantum field theories and he defines gluing as this left Khan extension thing. So I thought that was interesting.
Any other questions? Okay, if not, let's thank Khyathi again.